All right. So I did this in somewhat detail last time. I'm putting Sarah to sleep. Yawning makes me want to go take a nap. No. All right, so I did this in class last time. The basic idea is there's many different kinds of geometries. Don't panic. I could do something like this and say, what's the electric field right here? I won't because I would have to grade it. And I don't want to. But let's just talk it through. If I have a positive charge here and I'm looking for the electric field at this point, is that, first off, is this a possible question? Is there an electric field at this point due to those two charges?
Yes.
Yes. Which way is it from the positive? It's going to be directly away from it, so it's going to look like that. And what about for the negative? It's going to be towards it, right? So at this point, what you would have to do is put your coordinate system there, know the angles involved, add the x parts, add the y parts, blah, 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 take it back, give your final answer in polar form. This is totally a fair question, but it would take a lot of time and would take time away from other problems. So I will tend to stick to the kind of question I did last time. So I had a charge here and I had a charge here. I could have, this is what you actually pray for, because I would have a charge here and a charge here, and that's what it is right there. The reason for that is because then it's just, no, there's no angles. That's not like this. This is the one I did last time. Something like this, with slightly different geometry, I would say you can probably pretty much count on. You have an E1 and an E2. Know how to add those together to get a final electric field. And know that I could ask that for any point, anywhere, but as long as I put it on the x-axis, it makes the math a little simpler. And that's what I would tend to do, either on the y-axis or on the x-axis, right? Is that clear with what I'm saying here? Mm-hmm. Right? So I'd say, yes, that's one of the ones you want to be able to do. Shoot, I forgot to bring that paper. Give me a second, there was another one I wanted to. Oh, so problems where I have two charges of differing magnitudes and charge, and I ask you to find the locations on the line where the electric field is 0. Right? Do you understand the question? Yes. Right. So that's another one I would practice. But so let me just be clear then. If I have a charge here and I have a charge here, and this one's positive and this one's negative, where am I going? Oh, and this is big and this is small. Where am I going to look to find where the electric field would go to 0? And if you remember, I've labeled these as 3 regions where I'm to the left of both charges, between the 2 charges, and to the right. No, so there's a big positive charge and there's a small negative charge. It's going to be in region 3 to the right of the negative charge, right? Because in between, the field is pointing to the right by both of them, and over on this side, I'm always closer to the big charge. Close makes it bigger, and big makes it bigger, so the negative is never going to win on this side. It can only win on this side, and that's where you look. If they were both positive charges, where would you look? In the middle, because if I'm on this side, they're both to the left. If I'm on this side, they're both to the right. Here, they're both in opposite directions. It would be in the middle, but closer to the smaller charge, right? Everybody with me? So there would be something like that. So imagine this. Here's the question I could ask. I've got this line. I've got these 2 charges. Could I ask what the force is from first charge on the second charge? Yes. Fair question, right? We have everything we need. We've got the distance. We've got the 2 charges. I could ask that and say, what's F? What's the force of the negative charge on the positive? Or what's the force of the positive charge on the negative? Either of those are fair questions, right? Could I ask what the potential energy is of this system? This is the question, the potential energy. Could I ask what the potential energy of the system is? Yes, because U is K, Q1, Q2 over R, where R is the distance between the 2 charges. So I could ask that system. Could I ask, what is the electric field of this system? No. Because there's a different value for every location in space, isn't there? Could I ask, what is the potential of this system? No. V. Could I ask this, what's the V for the system? No. because it's a different value for every point, wherever place you put your finger. Remember that V and E there's only one charge in those expressions, which means that every location you look, you're going to have to add up the contributions from each charge that's in the system. Positive charge is positive potential, negative charge is negative potential. All right? So if I want to ask an E question, I need to say, what's the electric field at a point? Or I need to say, find the point where the electric field equals this. If I want to say, find the place where V is 0, could you do that? Is there such a place? Oops. I assume that's negative. Is there a place where V is 0? V is KQ over R. So is there some location where the contribution from the negative charge is the same size as the contribution from the positive charge?
Very close.
Yes. How many answers are there to that question? The reason is that as I get close to the negative charge, it gets arbitrarily large. So however big this is, I can get close enough to the negative charge on this side and on this side, such that it will add up to 0 with this. I can't do that with field because field has direction. The potential does not. Potential is just a scalar number. That's really critical to understand. All of life is critical, and everything I say is the most important.
You said potential is what?
Potential is the scalar. All right? So we've got those two. I'd say, and I'll give you a better example of this on Monday, but I'd say also that stuff we did with capacitors, I might ask a question which would involve finding the energy stored in a capacitor, finding how the energy changes under different circumstances. So let me just go with this. Given these two pieces of information, let's just start here. If I'm hooked to a battery, what does the battery give me that doesn't change? The voltage, right? So that won't change if I'm hooked to a battery. If I have this capacitor and I cut the distance between the plates in half, what happened to the capacitance?
Twice.
It doubles. Everybody see that? If I cut D in half, it's in the denominator, that means I've doubled. So I've doubled the capacitance, but I'm still hooked to the battery. What happened to Q? Be specific. It not only increased, it doubled. Right? Because if this didn't change, but C doubled, then Q doubled. Are you with me? Now I go back. Here's my capacitor. I disconnect the battery, and I move the plates. I cut the distance D in half. So I've doubled my capacitance. Now what happened?
Your voltage is coming down.
If I've disconnected the battery, what stays the same? Because I have no way off. Q stays the same because there's no way off. I've disconnected, there's no way off. So Q stayed the same, but I've doubled C. What happened to V? I doubled it. Because if you double the denominator, you cut it in half.
Right.
1/2, double the 2 is a 4. So 1/4 is half as big as 1/2. Play with this, all right? I shouldn't tell you this because you won't look at it ever again. I probably won't deal with the capacitors, with the kappas. I probably won't do anything with kappas. I did that because your homework has got that, but on test I probably won't put the kappas in there. But I will play with this idea, understanding with a parallel plate capacitor, which I would give you this equation. You need to know this, it's the definition. This is something you need to know. I'm not going to give it to you, you need to know this. And then, if I play with this, like if I make area twice as big, that doubles the capacitance. If I make the distance twice as big, that cuts it in half. So understand how those work. This is just a constant and doesn't change. All right, so the epsilon is just a constant that doesn't change. And so just know, if I mess around with A or D, how does it change the capacitance? And then there's two things. I can say, what happens if the battery stays connected? What happens if the battery doesn't stay connected? If the battery is connected, what doesn't change? D. If the battery is disconnected, what doesn't change? Q. All right? So that's kind of heads up on some of that. Start looking at it. Guys, I'm not going to lie to you. Next week is challenging. And you're saying it already is. I'm going to have a question on the test, which I'm going to do in laborious detail, probably on Wednesday. All right? I will show you how to do it. It's the kind of problem which everybody has to do at least once. And to tell you how this is going to be on the test, it's going to involve finding the amount of current that's flowing in a circuit. But I'm going to tell you the answers. I'm going to say the answers are I1 equals this, I2 equals this, and I3 equals this. And that way you'll know if you don't get those answers. Even on the test, I'm going to give you the answers. And your job is to show how to get those answers. So everybody makes algebra mistakes on these, everybody. So by giving you the answers, you'll know what stuff to go back and check. Does that make sense? Right. Have a horrible weekend because you'll be studying for physics and other things all weekend long. All right. In other words, what we're trying to find is when's the equal to that match. What you want to do is that E is equal to I tell you this, you just have to solve it. That's not one.